Okay, hi. For this video, we will be discussing the introduction to differential equations. So for the outline of the presentation, so we have first the definition, and then we will be discussing the classification of differential equations, order, degree, and linearity of differential equations, the solution of differential equations, elimination of arbitrary constants, and we will discuss the origins of the differential equations or the applications. So first, we have an ordinary differential equation. So a differential equation is an equation containing an unknown function and its derivatives. So we have here the examples. Okay, so as we can see here, so it's an equation containing a derivative. Okay, so for the first one, we have dy over dx is equal to 2x plus 3. So we have here a first order derivative. For our second example, so we have this one. So as you can see, we have a second order derivative and a first order derivative. Okay, and then third, we have a third order derivative, a first order derivative, and so on. So any equation containing differentials or derivatives are called differential equations. So it's an ordinary differential equation if it only has one independent variable. Okay, so the variable, okay, in the denominator of the derivative, so that is the independent variable. So x here is the independent and y is the dependent variable. So partial differential equation is or are differential equations where we have two or more independent variables. Okay, so we have here an example. So the second derivative of u with respect to x plus the second derivative of u with respect to y is equal to 0. So as you can see, the denominators are different. We have x and y variables. Okay, so we have two independent variables while we only have one dependent variable. Okay, so it is also noticed that the way we write d, okay, so this one, so the way we write d is like this. Okay, so it's like an inverted number 6. So if you see this differential sign, okay, so it's partial differential equation. Okay, so it's another way to what do we call this? It's another way to distinctly identify. Okay, so identifying partial differential equations. So when we see the d written like this, so automatic it's partial differential equation. Okay, so we have here other examples, sorry. So other examples of partial differential equation. So as you can see here, x and t, then x and t, so we have two independent variables. So it could be 3, 4, or 5 and more independent variables. It depends upon the equation. Okay, so the order of the differential equation. So when we say order of a differential equation, it means that it is the highest order of the derivative in the differential equation. Okay, so the order of the derivative is the first derivative, second, third, fourth, fifth derivative. So it's the order of the derivative. So the highest order of the derivative will define the order of the differential equation. So say for example, we have dy over dx is equal to 2x plus 3. So as we can see here, the highest derivative is the first derivative. So therefore, its order is 1. For the second, so the second derivative of y with respect to x plus 3 dy over dx plus 9y is equal to 0. So as you can see, the order, the highest derivative is the second derivative. So therefore, its order is 2. And then, oops, spoiler. So, and then, for the third one, so we have here the third derivative, we have here the first derivative, then its order is 3. Because the highest derivative is a third derivative. Okay, so for the order, all we need to do is find the highest ordered derivative. So for the degree of a differential equation, so the degree of a differential equation is the power of the highest order derivative term in the differential equation. Okay, so first we look at the highest order derivative, okay, and then look at its exponent. So we have this one, this differential equation. So as we can see, the highest derivative is the second derivative, okay, and its exponent is 1. So I'm not sure if this has a pen. Okay, so let's have, so as we can see, the first derivative, actually we have an exponent of 1, right? So which is invisible. So it can be call this, we can choose not to write it, okay, because it's obvious. Okay, so its degree is 1. Okay, so in the second example, so the degree of the differential equation here is still 1 because we look at the power of the highest order derivative. So the highest order derivative is the third derivative, and its exponent is 1. Okay, so for the third example, so the degree of the differential equation here is, again, we look at the highest order derivative and then its exponent. So its exponent is 3, therefore the degree of this differential equation is 3. Okay, so next is the linearity of differential equations. So a differential equation is linear if it follows the two conditions. Okay, these two conditions. So first, independent variable and its derivatives are of degree 1. Okay, so the exponents of the derivatives are all 1. Okay, and coefficients of a term does not depend upon the dependent variable. Okay, so in this case, the dependent variable is y. Okay, so the coefficients here, coefficient of the derivatives does not depend upon y, okay, or the dependent variable. So example, so we have d squared y over dx squared plus 2dy over dx plus 9y is equal to 0. Okay, so this is, so are the dependent variable and its derivatives of degree 1. Okay, so the derivative, its degree here is 1. The degree here is 1, dy over dx. And here y, so the degree is also 1, right? So it's 1 there, and then here it's raised to 1, and this one it's raised to 1. Okay? Next is coefficients does not depend upon the dependent variable. So we look at the coefficients here. So the coefficients of the terms are does not depend upon the dependent variable. So therefore this is linear. Okay. So the next, so we take a look. So the derivative and its the variable and its derivatives are of degree 1. So as you can see, the second term here is raised to the power of 4. So therefore, this is nonlinear. For this one, so the derivatives are of degree 1. Okay. However, the coefficient here, so this coefficient is dependent upon the dependent variable. So therefore, this is also nonlinear. And for our last one, so dy over dx is of degree 1. However, sin y is nonlinear because sin y is y minus y cubed over y prime and so on. So therefore, this is non-linear. Okay, so as you can see, we already have, if we substitute y minus y cubed over 3 factorial, if we substitute it here, so we will already have a variable, a dependent variable of degree 3. And then we will be and then it will not comply anymore with the first condition, that the dependent variable and its derivatives are of degree 1. Okay, so this will be given as an exercise to you. So you need to complete this table. Okay, so first order differential equation. So we will start with this one. So we will be dealing a lot with first order differential equations in the first part of this course. So we have here the derivative form, differential form, and general form. But basically, first order, this is ordinary differential equations. So we will be dealing with how to solve for first order differential equations using different methods. First order again, so this means that the highest order of derivative that appears on the differential equation is 1, or the first derivative only. And we have nth order linear differential equations, which are also very common. Okay, so it's linear, okay, differential equations basically. And nth order, so meaning it's the highest order that appears in the linear differential equation. So we already know how to identify linear differential equations. Then if we encounter those, so we can identify already what linear differential equations are and solve them. Okay, so for the solution of differential equations, so the solution of differential equation is a relation connecting the independent and dependent variables which satisfy the equation identically. So that is for all values of the independent variable. So basically, this is the relationship of the independent and dependent variables without the derivatives. Okay, or you can think about it as the original function before it was derived. Okay, or basically what we do in integration, right? So the solution of differential equations are actually products of integration. Okay, so it's basically just integration. So That's why you should have deep knowledge of your integral calculus. However, not all differential equations can be solved directly by integrating. Okay, so that's why we have to study the different types of differential equations because um, because as I've said, we need some other steps, okay, in order for us to find the solution of differential equation. So it's not straightforward integration, okay, but integration still is part of the solution of differential equations. So we have two types of solutions. So we have the general solution and the particular solution. So a general solution contains a number of arbitrary constants equal to the order of equation. So since we'll be dealing with first order differential equations first, so therefore the general solutions that we will be obtaining for the first order differential equations is only one, okay, for each differential equation. So again, the number of arbitrary constants is dependent upon the order. So the particular solution is obtained from the general solution by assigning particular values to the arbitrary constants. Okay, so but basically for particular solutions, we have the conditions of the independent and dependent variables, and from there we can solve for the arbitrary constants. So we'll have examples of those later. Okay, so it's this. So this is an example. So y is equal to 3x plus c is the solution of the first order differential equation. So this. Okay, so this is the solution. Okay, so actually what we do is this is a variable separable type. So we have dy. Okay, so I'm having difficulty writing in PowerPoint using my mouse. So dy over dx, right, is equal to 3. So separation of variables, so all we need to do is cross multiply 3 on the other side. Oh, sorry, multiply dx on the other side, cross multiply, so we will have dy, sorry, dy is equal to, is equal to 3 dx. Okay, so again, solution of differential equations require us to integrate, so integrating both sides, so integral of dy is equal to integral of 3 dx. Okay, so dy, integral of dy is y, right? So y, what happened? So y is equal to integral of 3 dx is 3x. Okay, and since we have integrated, so therefore we will have plus c. So the c here now is the c now is the arbitrary constant, and y is equal to 3x plus c is the solution of the differential equation. Okay, so here the c, or the arbitrary constant, is not known, it's unknown, so therefore this is a general solution. Okay, so we solve for the particular solution if we assign values for y and x. Okay, so this is given in the conditions of the problem. So if we substitute values for y and x from given conditions, then we can solve for c, and if we already know the value of c, then it will now be called the particular solution. Okay, where's that? So this one, this particular solution, so it's called a particular solution if the arbitrary constant is known or already solved. Okay, so we have families of solution. So it's just an example of a differential equation, okay, and its solution. So for this one, this is the differential equation, okay, and then this is its solution, okay. So where this is a solution, the solution is a family of ellipses, okay. So because we have a known c, okay, so therefore the ellipse may have different values for its, what do we call this, its minor and major axis. Okay, so origins of differential equations. So it can have geometric origins. So these are already the applications and the applications of differential equations and how do they occur in nature. So we have the geometric origin of differential equations. Okay. So for the family of straight lines, so the differential equation is this. The second derivative is equal to 0, and so on. So I will be posting this PowerPoint presentation in our course so that you can view it. We have physical origin, okay, so it can be applied in free falling bodies, springs, okay, so this is the differential equation for the springs, and we will study those, what do those equations mean physically. And we have RLC circuit, okay, so this one. We also have the Newton's law of cooling, growth and decay, and that's it. So those are the physical origins, okay. So those basically are some examples of the origins of differential equations, okay, and those will be the applications that we will be discussing throughout this course. Okay, so that's all. So kindly answer the exercises, okay, and identifying the order, linearity, degree, the classification if it's an ordinary or partial differential equations, and then list all the independent and the dependent variables. Okay, so that's all. So see you in the next lessons.